IR spectroscopy. Spectroscopy methods are very important in organic chemistry because without these methods, it will be impossible to discuss any organic structures in books or in a papers or in a class for that matter. And we have four common spectroscopic techniques which we'll be looking today, but of course we'll be focusing on IR spectroscopy for this lecture. And this IR spectroscopy is one of the spectroscopic techniques used to determine functional groups, and this IR spectroscopy works by using the IR region, by using IR region, the electromagnetic radiation in the IR region. So in the light you see you have high energy radiation and low energy radiation, which the visible one is a high energy radiation and the indivisible low energy one is the infrared region. So IR being among one of these important spectroscopic techniques in organic chemistry, but also we use NMR, one of the powerful structural elucidation methods, which is helpful to determine the environment of carbon and hydrogen in a given organic molecule. It works by excitation of a nucleus. Simply when electromagnetic radiation at radio frequency hits a molecule, its nucleus tends to spin. That spinning feature is interpreted by the detector and transformed into structural representation. In IR, the infrared radiation hits a molecule and creates a vibrations or triggers a vibrations. From those vibrations, it is possible to determine the presence and the absence of functional group. Whereas, while in mass spectroscopy, a sample is hit by a bombardment of electrons, which is made to fragment, and by collecting the information from each of the fragments, we can be able to determine molecular mass and atom connectivity in that structure. In UV spectroscopy, which is higher in energy than IR, what happens is that the UV radiation actually makes the electrons in the molecule to excite from lower energy level to higher energy level. That excitation tells us whether or not we have the conjugated pi systems like double bonds and triple bonds. So IR spectroscopy, like any spectroscopic techniques, works by interaction of the sample or matter with the electromagnetic radiation, the infrared radiation in our case. From that, chemical nature and molecular structure of a molecule is determined. You can have IR radiation, IR electromagnetic radiation in the form of absorption, emission, or reflection, but in organic chemistry, we use absorption IR to determine structures of organic materials, polyatomic inorganic materials, or organometallic compounds for that matter. So the electromagnetic radiation is a form of energy. So electron, you can define electron as a particle or as a wave. So this electromagnetic radiation, when it is considered as a wave, as a particle, the particles are considered as a photons. And each of these photons has discrete energy called quantum. In these spectroscopic techniques, electromagnetic radiation is expressed in terms of wavelengths and frequency. The wavelength is simply the distance between two wave points in a emerging wave, whereas the frequency is the number of waves passing per unit time. Normally, we use a meter to angstrom when we measure the wavelengths. You can see nanometer, micrometer, but most of the time from micrometer to angstrom. And these wavelengths and frequency are related in a kinetic energy formula, which is given as HV. We'll look at this formula later in one of the slides. So what does happen when a matter interacts with electromagnetic radiation? Well, it depends based on the energy of that radiation. Lower energy radiation, such as the radio frequency, will make the molecule just to spin around its axis, whereas high energy radiation, like that of the near UV, it makes the electrons within the molecule to excite into high energy levels. So as energy increases, so does frequency, but the wavelengths decreases. So in high energy we will have very short wavelengths. So the interaction differs, so does the characteristics of the molecule as a response to this radiation. If you apply X-ray radiation to a molecule, what happens? It detaches the electron from the molecule, and it can make the molecule from neutral to a charged form. That's what happens. So this is actually what electromagnetic radiation does to molecules. And a set of all this electromagnetic radiation is called electromagnetic spectrum, and a small section from about 400 nanometer to 750 nanometer is only for the visible light region. And as we increase the energy, so that the frequency, whereas the wave number, or the wavelength decreases as opposed to energy and frequency of the electromagnetic radiation. So let's take back again to the kinetic energy formula, which is given by Planck's constant times frequency, whereas the frequency is given by speed of light or velocity divided by wavelengths. If we insert that into the above formula, you can find the kinetic energy is given as Planck's constant times speed of light by wavelengths. So the wavelength is simply a distance between two identical waves, whereas the speed, the c, is the velocity of the light passing at a time unit. Infrared radiation will have a wavelength between 2.5 to 17 micrometer and a frequency between 4,000 to 600 centimeter inverse. Because this range is similar to the bond frequencies of a covalent bonds, IR is used to determine the kind of a covalent bond present in the structure, and also to deduce some other structural information from the spectrum that appear. So what does the frequency V depend on? So there is this model that considers a covalent bond as a spring, and in that model it converts the kinetic energy formula into uh, uh, into a subatomic way, that the kinetic energy is now Planck's constant times half pi times radical of the bond strength and the reduced mass. So we have two atoms connected by a covalent bond, two atoms with a different mass. The frequency of this molecule containing these two atoms with a different mass is proportional to the strength between the bonds, but inversely proportional to reduced mass between these two atoms, and that is displayed in the formula you see in the slide. Let's support this with an example. If you take a look in the first case, the carbon, hydrogen, carbon, deuterium, carbon, carbon, the number of the size of the bonds is, the size of the atoms sharing the bond is increasing downwards, whereas if you take a look at the measured frequency to the right side, the frequency is decreasing. Whereas in the case of bond strings, as we go from the carbon-carbon single bond, which is weaker compared to carbon-carbon triple bond, the bond strength increases as we go downwards, so that the frequency. That's why we said frequency decreases with increasing atomic weight, but it increases with increasing the bond energy. So this is what I said about the model that considers the bond as a spring. The important information here is an electromagnetic radiation induces certain vibrations in a given molecule, but those vibrations are not the same for every molecule. It depends on the nature of the electromagnetic radiation and the nature of the molecule, of course, because if we are talking about infrared radiation, then the difference will be depending on the nature of bonds between the bonding atoms. So vibration modes, depending on the nature of the molecule and the bonds within the molecule, the molecules can display different vibrational modes. They can display all of them at the same time, and most of the time they display most of all of them at the same time, but that doesn't mean all of them are detected by the IR. From what I know, mostly the stretching and the bending are mostly detected by the IR. But of course, as you can see, for a typical water molecule, the bonds can stretch in the same direction, which is called symmetric stretching, and whereas the bonds can stretch in alternate way, where one of the bonds compresses, other stretches, and vice versa, or the bonds can also bend. These vibrational movements are detected in the IR detector to estimate the structure of the molecule under study. So the IR spectroscopy does only these vibrations because of its lower energy. The higher the strong that it can does to a molecule is it creates vibrations and different vibrations like that of water molecule we saw in the previous slide. So a given molecule tends to display these vibrations if the frequency of the radiation matches the vibrational frequency of that molecule. Then those radiation modes can be observed in a molecule. Then IR spectra is expressed as in terms of percent of the light transmitted as a function of energy of the light that is observed by the molecule. So samples that absorb all of the IR light would give a spectrum with a horizontal line near the bottom of the spectrum. But all samples does not absorb IR light, and we will discuss this in detail in the coming slides. So when a source of IR is released into a chemical sample, what happens is some of the IR is absorbed within a molecule, whereas some of it is transmitted through the molecule, and this transmitted light is absorbed by the detector and interpreted in terms of the structure of the molecule. In fact, the detector can estimate how much frequency is absorbed by the sample by manipulating the amount of the transmitted light that reaches into it. Well, we can have IR in absorption mode or in transmission mode. They are the same, there are also somewhat different. In absorption mode, the IR spectrum is given with percent of absorption against frequency in wave number, whereas in transmission mode of IR spectrum, the spectrum is given in terms of percent of transmission with respect to frequency in wave number. If you had a chance to see at IR spectrum from books or from any papers or from your lab manual, most of the time the transmission mode of IR spectrum is commonly applied, and we will also be discussing using this mode for organic molecules in this lab lecture. IR bands can range from strong to weak. This depends on the nature of the bond. Some bonds have weak bands, other bonds have strong bands. Normally the strong bands are very tall and they almost occupy most of the y-axis, whereas the smaller bands can range from like flat to 1/3 of the y-axis. Bands Bands can be strong to weak and not observable, of course, depending on the nature of the bond. The nature of the bond that has to do with polarity is the most important thing here. Compounds with strong polar bond, with strong bonds, will have strong bands, whereas compounds with weak polarity will have weak bands. In covalent compounds, the polarity of the bond is determined by the difference in electronegativities between the bonding atoms. If you see, electronegativity of oxygen is higher compared to carbon in the first structure, in the carbonyl carbon structure, whereas if you see in the terminal alkyne with weak bond, you can see the carbon-carbon have the same electronegativity, so therefore there is no any such significant electronegativity difference that makes the bond to be nonpolar and bear weak bands when measured in IR or when seen in IR. Bands can also be broad bands or sharp bands or narrow bands. Most of the bands are narrow, that range from weak to strong bands, whereas some functional groups, specifically the OH bonds, which you can see them in water, alcohol, or carboxylic acid, usually have the broad band, this kind of band. And when you see the spectrum, if you see this band around 3000, it simply tells you there is OH group in the structure. So what information do we obtain by looking at the IR spectrals? First thing is, the purpose of this spectroscopy is to determine the functional group. So with respect to transmission percent and wave number, each functional group appears at different wave numbers. So if you take those ranges, which are expressed in wave number per centimeter inverse, you can see what you will be able to distinguish what functional group is this or what functional group is that. So the IR spectrum in general is a molecular fingerprint that we can compare with the IR spectrum of our own samples. So normally we have a database of pure IR spectrum of a pure compound, which if a student claims that he synthesizes a given compound, and if the IR spectrum of that newly synthesized compound and the pure compound are the same, that the student can simply conclude that he has got the same compound. However, because of the energy limitation, IR can give you the range of different functional groups in fragments, but it doesn't give you the molecular formula of those fragments. And that's why IR should be used in integration with other spectroscopic methods like IR, UV, and MS in order to have fully elucidated organic structure. A fingerprint region. A fingerprint region in IR is an observation that goes from 1500 to 400 centimeter inverse. Normally, unlike the absorption above this range, this absorption is very specific to a specific molecule. So to simply explain it with an example, if you take one propanol and 2-propanol, where the OH is in the middle carbon, and in the former case where the OH is in the first carbon, in the second carbon. So when you measure IR spectroscopy in the range above 1500, you'll see almost similar thing. However, if you compare the fingerprint, 1-propanol is different from 2-propanol because the position of the hydroxyl group is different in that organic compound. You can only identify this by looking at the fingerprint region. In fact, the whole IR spectrum can also be used as a fingerprint region because, like I said before, if you compare the IR spectrum of a known compound with IR spectrum of known compound, if they are the same, it means a known compound is that compound, right? So that's also another way to say that the IR spectrum is a finger region in the fingerprint region at the whole. So the IR absorption spectrum ranges from the fingerprint region to the normal region, and it entirely includes from 4000 to 600 centimeter inverse. So for simplicity, these absorption ranges are also given in tables sometimes in figures like this, and they will help a lot, specifically if you are doing a research. They'll tell you fast what that compound would be. We use this data often in the lab, and you can also see that in many organic textbooks they print these ranges at the back side of their books, and because it saves a lot of time. So normally if you see at these ranges, if you see an IR band between 800 to 1800 to 1600, probably you will suspect either it is carbon-carbon double bond or carbon-oxygen double bond or carbon-carbon nitrogen double bond. However, to clearly sure whether it is carbon-carbon double bond or carbon-oxygen double bond, you have to support your argument by looking at the fingerprint region. And now let's see IR spectrum of individual functional groups in organic chemistry, beginning from alkanes. Alkanes, as you know, are saturated compounds with no any functionality. So you will have only carbon-carbon single bond and carbon-hydrogen bonds. The carbon-carbon single bond is totally non-polar because carbon and carbon are similar, and it doesn't help us to distinguish the structure of an alkane, but there is slight difference in electronegativity between carbon and hydrogen. That's why the carbon and hydrogen bonds absorb at about 3000 centimeter inverse in the IR. If you take a look the spectrum below for N-hexane, you will see the CH bonds, the stretch of this alkane have absorption at a range between 3000 to 3800 or 700. So alkenes differ from alkanes in that they possess a carbon-carbon double bond. As a result, there is a distinct sharp band in the range between 1600 to 1700 in the IR spectrum. But of course, the alkene can contain hydrogen, like the vinyl hydrogen, which means the hydrogen is connected to a carbon bonded to a double bond, and as a result it will have an absorption around 3080 centimeter inverse in the IR spectrum. Sometimes this CH absorption can be masked by other peaks if these peaks are more broader than the CH peak itself. Let's see that example in the next slide. So if you see here, it's a cis-2 octene. However, the CH of vinyl, the vinyl hydrogen, the CH that occurs around 3023 is masked by the broadband peak appearing between 3000 to 3080 in the IR spectrum. Okay, whereas you can clearly see that we have the absorption for the carbon-carbon double bond at 1660 in the spectrum. For alkynes, again, alkynes and alkenes are almost similar. The only difference is alkynes have another pi bond in addition to the double bond, and because of that you will have an absorption at 2100. However, this 2100 is, if you see, is less than the carbon hydrogen absorption. Clearly it's because of, even if it is triple bond, still the bonding atoms are carbon and carbon, and you can see that because we said frequency is inversional relationship with the reduced mass, you can see that this carbon-carbon double bond have lesser absorption compared to carbon-hydrogen bonds. Alkynes can be middle alkynes or terminal alkynes. In the middle alkynes, there is no chance that we will have hydrogen because the carbon will be fully saturated. Whereas in terminal alkynes, where there is one carbon atom in the end to the carbon atom that is triply bonded with the other carbon atom, you can have hydrogen. And this hydrogen, because of the rich electrons in the triple bond, will be more polar, okay, more acidic. And that's why you see carbon-hydrogen polar bond and absorption in IR spectrum at around 3300 centimeter inverse in the IR spectrum. Let's see this example in the next slide. So in the above one, it's a terminal an example for terminal alkene, which is 1-octane, and you can clearly see that we have this kind of vinyl hydrogen or vinyl alkyne having absorption at 3313, whereas there is no such carbon hydrogen stretch in the middle alkyne, and you see there is no any peak. I mean, there is no such a significant peak occurring in the 4-octane, which is presented as an example for middle alkyne. Right. Nitrile. Nitriles are corresponding nitrogen containing triple bonds, the carbon nitrogen, where the triple bond exists between carbon and nitrogen. So you see that the absorption is a little bit increased by 115 compared to the absorption of a given alkyne. That's simply because the difference in polarity between carbon and nitrogen. And you can see that this absorption normally occurs at around 2250 in the spectrum, which also means the other alkyl groups connected to carbon will absorb at around 300 for the CH stretching, or below 1600 for CH bending. Alcohol. So do you remember that alcohol has distinct band compared to most of the bands in organic chemistry? And if you see, that's a very interesting broadband here for the OH, which you can see it between 3000 to 3300 to 3500, and that is a distinct feature for the alcohol. Okay, normally this broadband, so if you measure at the tip, it will be around 3300, but because it's a broadband, if you measure from the base of the peak, it will be from 3000 to 3700. Aldehydes and ketones are often discussed carbonyl containing functional groups. They are the same in that they contain the carbonyl carbon, and this carbonyl carbon in both aldehydes and ketones has an IR absorption between 1710 to 1720 centimeter inverse. However, aldehyde and ketones are different in their structure because the carbonyl carbon in ketones is in the middle, whereas the carbonyl carbon in aldehydes is in the terminal. Therefore, ketones lack the CH bond, which occurs in aldehydes. That's why aldehydes have an additional peak that appear between 2700 to 2800 in their spectrum. Let's see the butyraldehyde and the 2-heptanone. In the above aldehyde and aldehyde example, you can see the CH stretch appearing at around 3500, whereas in the below there is no any CH stretch appearing, right? There is no any prominent peak appearing, while because both these carbonyl compounds have the carbonyl carbon, you can see the carbonyl carbon absorbing at almost similar absorption, which is 1718 for the keton and 1720 for the aldehyde. Another interesting functional group is the carboxylic acid. It's interesting because it contains two kinds of functional groups, the carbonyl carbon and the OH carbon. Similar to the alcohols, the OH will be absorbed between 2800 to 3800 in a broad band, whereas the carbonyl carbon will absorb between 700 to 1700 to 1710, and specifically for hexanic acid, this carbonyl carbon absorbs at 1710 centimeter inverse. Amines. Amines are another organic compounds with many industrial applications, and amines are derivatives of ammonia, where one of the hydrogen is replaced by R group. In this case, they can be primary, which means only one hydrogen atom is replaced by R group. So these primary amines will have 2 hydrogens. The nitrogen-hydrogen bond in amines is polar, more polar than any other compounds, but a little bit less polar to the OH bonds in alcohols. Therefore, it will have significant peak in the spectrum. And unlike any other compounds, what you see is if the amine is primary, you will have 2 spikes existing in the spectrum, whereas if the amine is secondary, which means only 1 hydrogen that is connected to nitrogen is available, and then you will have only 1 spike. So this 1 spike normally, most of the time, scientists resemble it to a canine tooth, to make it simple to remember. Amides are corresponding derivatives of carboxylic acids. In fact, their IR spectrum resembles that of the carboxylic acids, because even not broadband, but you will have an absorption of the amine with, in fact, with 2 spikes here between 3100 to 3500, and an absorption for the carbonyl carbon between 1630 to 1660. Well, that's all I have for the pre-lab lecture in amines. And if you find this video important, you're free to like it. And if you have any question also, you can ask me through my email, or you can put in the as a comment in my YouTube channel. Thank you for your time.